Okay, good afternoon. Can you hear me? Can you all hear me? If you can hear me, please, someone please let me know whether is it clear? Can you all hear me? Okay, so yeah, looks like still people are joining. Let's wait a couple of minutes. Until we are waiting, I will recap what we have done last week. Okay, so let me share my presentation. Okay, so yeah, because it looks like still people are joining, therefore I will recap what we have done last week. So last week we started with the sampling part. So the sampling, we discussed what is known as the sampling, what is the definition, and what are the types of samples and the steps involved in the measurement process. And also we define this gross sample, all the terminologies. So you should know these terminologies, what gross sample means, laboratory sample. And we discussed about the sample size, how the samples, when we change the size, how the analysis type is changing. And also we discussed about how we can collect some samples of solids. So solid sampling and available methods and available instruments for solid sampling. And also powder, how to do the sampling from powders and metals and biological samples. And also we discussed how we can reduce the sample size, the methods. And this one also, sampling of liquids, also discussed last week, the available techniques for liquid sampling. And we stopped here. So the sampling of gases. And this lecture, I think, I don't know whether you went and have a look the LMS. If you look that one, I uploaded this lecture notes today, and also it comes under sampling section. So the sampling section, the last week lecture notes as well as today's lecture notes will be there. And also the instrument performance characteristic part, that one also you can find when you log into the LMS. Okay, today let's start with this sampling of gases. Let's see how we can collect gas samples. Okay, the gases, why we need to do the gas sampling? One major reason is when we need to assess the air quality, we need to collect those gases. So, for example, when there may be some industry and workplaces which has lot of air pollution. Therefore, when workers do their work at those type of workplaces, these workers are exposed to lots of hazardous gases and vapors. So these exposure need to be categorized and measured analytically. The reason is, if these workers exposed to a lot of hazardous gases for long period of time, they will end up with some illnesses, some health issues. So if if there are some health issues, it is a problem to the employees as well. So employers are also have some problem. Therefore, the assessment of air quality at workplaces is really important. When we talk about the gas sampling, sometimes grab sample is okay. So what is the grab sample? Grab sample is the sample which has all the test materials which can be collected at one time. We discussed about this last week. So normally liquid samples can be considered as grab sampler, but the solid samples are not grab sampler because it is a heterogeneous mixture. When we talk about the gases also, most of the cases gases form homogeneous mixture. Therefore, a grab sample is okay, right? And let's discuss what are the techniques available for gas and vapor sampling. There are 4 major techniques. The first one is gas sampling vessels, and the second one is static sensors, entrapment, and real-time analysis. We will discuss these 4 techniques in details in coming slides. So first, let's discuss gas sampling vessels. So the name also implies here we use kind of vessels to collect the gas samples. So these vessels can be either glass or metal. Most of the cases, you can see in the picture also, stainless steel is used as a metal here. Normally, the capacity of this gas sampling vessel can be in between 0.01 to 10 liters. So 0.01 means 100 milliliters to 10 liters. So the capacity has huge variation. So we can, depending on our purpose and depending on the nature of the surrounding air, we can determine which type of vessel that we have to use. And another thing is, these vessels should either evacuated or flushed with gas before sample collection. The reason is, we are collecting air, right? Therefore, already there are a certain amount of air inside these vessels. Therefore, first, before we collect the samples, first we need to either evacuate. We can evacuate the vessel and then we can collect the gas sample. Or we can flush with the sampling gas. We can flush with some gases before we collect the sample. Because when we flush with the gas that we are analyzing, now the vessel, the available gas can be replaced with the gas we are flushing. So we have to do one of these things before we collect gas samples to this gas sampling vessels. And these gas sampling vessels are reliable for high concentrations of gases. So that is one disadvantage, or it is one limitation for this gas sampling vessels. It is reliable only for high concentrations of gases. If we have to analyze really small amount of gas, it is really difficult to use this gas sampling vessel because it is reliable only for high concentrations of gases. You can see in this picture it has inlet and outlet. Normally when we do the sampling, we can connect some let's say some tube or something to this inlet, and then we collect from here to here. And this outlet can be used to remove the gas from the cylinder. And for direct sampling, that means when we directly collect the sample, we can use this gas storage vessels, or there's another thing called gas sample bags. So the commercial name is Stedler bags. That's the commercial name we are using. So we can use this bag. So you can see in this diagram, it shows the Stedler bag, image of a Stedler bag. We can use this type of bag also for gas sampling. So here there are some inlet, air inlet, and we can collect some tubing to this bag also. So see, the bag is connected to pump, and air is drawn at 1 to 3 liters per minute. So that flow rate is really important because you can see in the third point, volume equals to the flow rate times time of sampling. So based on this equation, according to this equation, when we change the flow rate, we can change the volume, and we can keep the time fixed, and within a fixed period of time we can determine what is the volume that we are going to collect by changing the flow rate. Or there's another way, we can fix the flow rate and we can change the time of sample collection. So all these things depends on what we have to do, what is our purpose, and what we need to analyze. So all these things have to consider when we do this gas sampling. Okay. And liquid displacement method to collect gases. That's the most common thing. I think when we all were kids, we use that method. We use some bottle or some, let's say, if it is in the laboratory, in the basic elementary lab, we can use some boiling tube or test tube. And then what we did, we just put this test tube filled with water in the upside down direction, and then we collected some gases, right? If you can remember, there's an experiment called hydrilla tree experiment. So we put a funnel and kept the inverted boiling tube, and then we collect the evolving gas. So evolving oxygen, we collect it. So that's the liquid displacement method. So we displace liquid from air. So that one also possible. We can collect gases from that method also. But in that case, we have to consider two things. The collecting gas should not react with the liquid. The reason is, if the gases react with liquid, then we cannot collect the gas, and we cannot analyze the gas using the liquid displacement. And also the gas should not soluble in the liquid. That's another important thing. If the collecting gas or the gas that we are interested in, if it is soluble in the liquid, so then it's also has no point, right? So that's another method of collecting gases. And here the breath sample. So the breath sample, that means the sample we breathe, that one also we can collect. In that case, the person blows into evacuated bag. So we can take evacuated bag and give to the person, and we can ask that person to blow into that evacuated bag. By that, we can collect the breath in that particular person. Okay. The next one is static center. So we discussed the gas sampling vessels, and the second one is static sensors. So when it comes to the static sensors, there are two forms of static sensors. Normally in the industry, there are two types of static sensors. The first one is Adsorbent Sensors and the second one is Electrochemical Sensor. So let's see what is Adsorbent Sensor means. In the Adsorbent Sensor, the adsorbent material, so the absorbing material exposed to air via a semi-permeable membrane, right? In that case, a semi-permeable membrane has been used. So semi-permeable membrane means it has some partial permeability, and some kind of absorbing material will be placed in a kind of container. We can say it's a container. So some absorbing material is there. So and the semi-permeable membrane, and the gas will pass through that membrane, and it will go to the absorbing material, and it will absorb to the absorbing material. See, the analyte gas, it reaches the adsorbent material via diffusion. So diffusion is the technique. That is how the analysis gas reach to the adsorbing material. And the workers can wear this device during working hours. So now we are talking about how we can determine the air quality in a workplace, right? So that's the mostly utilizing thing for this gas sampling. So these workers can wear this adsorbent material or the adsorbing sensor during their working hours. So what is happening when they expose to a certain gas for a longer period of time, after certain threshold value, there will be a color change, right? So let's say the color will change from green to red. So if the person sees the red color, that means he should go away from that particular place immediately. The reason is if he exposed to that particular air more than that limit, then he will be in trouble. So that one can be used as an indicator how long, whether the person should stay in that particular workplace or whether he should move from that particular place. So in here, in the adsorbent sensor, adsorption is the mechanism, or the adsorption is the sensing mechanism. And the second one is the electrochemical sensor. So the name also implies something, electrochemical. So that means there should be some electrochemical reaction, right? So in this electrochemical sensor, it gives quick response, because there will be some oxidation reduction reaction happens there. Therefore, it will give some quick response than the adsorbent sensor. The good example of the electrochemical sensor is breathalyzer for measuring alcohol in breath. You all know the policemen use this alcohol detection experiment. They are doing some balloon thing, so we call it as breathalyzer. So that one has an electrochemical sensor. Actually, we will discuss it again in this entrapment also. Even though there are four different types of the gas collecting ways, sometimes they are interconnected each other, right? So here the breathalyzer is an electrochemical sensor, and also it comes under the next one. It's an entrapment technique, right? We will discuss that one later in detail. So that's the static sensors. That's how we can analyze gas using static sensors. The third technique is entrapment. So entrapment is also use adsorption process to collect the analyte of interest. So it traps the analyte, right? So there are some different types. The first one is the liquid traps. So Here the gas is trapped by a liquid. So in the liquid trap, gas will be trapped by a liquid, and gas is drawn through a bubbler or impinged by a pump. We can either pump or we can either bubble or impinge by using a pump. So then the gas will trap inside the liquid. And we discussed in the static sensor also the adsorption and the entrapment also. There are some solid adsorbent. So the one example is adsorbent bed of granular silica gel, onto which is poured a reagent that react with analyte gas. So we have some granular silica gel, and that silica gel will be coated with a reagent. So that reagent will react with the analyte gas. After the reaction of this gas with that reagent, it will produce a color. So it will also give a color change. Based on this color change, we can determine whether the gas is present or absent. Right? And the contamination level is determined by the length of colored stain in the tube. So when the contamination is high, the length is high. Therefore, depending on the length of the colored stain, we can determine the contamination level. And we discussed this one earlier in the earlier example also, the principle. This principle is used in breathalyzer tubes. What is happening there? Ethanol in breath, because when we drink some ethanol, our breath contains some ethanol vapors. Then when ethanol will oxidize by dichromate. So there, around the silica gel, dichromate has been coated. So this ethanol will react with the dichromate, because initially the dichromate has some orange color. Because of the reaction with the ethanol, it will form chromate. When it forms chromate, it gives a green color. Therefore, the color will be changed from orange to green. Then it gives an indication, okay, this person has drunk some ethanol. So that's an example of entrapment also. Okay, the next one is real-time analysis. So this analysis is instant or near-instant analysis. This real-time analysis is the analysis of data. Normally we can analyze data as soon as that data becomes available. If we tell it in other words, any user can get insight or can draw conclusions immediately after that data enters the system or instrument. Right? There are the listed here are some examples of the real-time analysis. The first one is electrochemical sensors. So electrochemical sensor use the gas phase electrolytic cell. So it will oxidize or reduce. And the infrared spectroscopy. So here the gas monitoring will be done by using IR detector. And the chromatography is also another real-time analysis technique. Here to analyze the gas, people can use gas chromatography. And there are some special sensors for detecting special gases. For example, there are some luminescent monitors for sulfur dioxide. And to detect ozone, some gas liquid chemiluminescent monitor. So those are some special sensors. But these three, electrochemical sensor and IR spectroscopy one and the GC, gas chromatography one, are the mostly used way or methods in the real-time analysis. So in the normal analytical lab, we use these most of the cases we use gas chromatography to detection of gases, right? So those are the four main techniques available for the gas sampling. And here next, let's discuss measurement principles. So the measurement principles, this one is also similar to the what we discussed earlier. So you will feel like we are repeating same thing. So it's okay. I will quickly go through these measurement principles, because under the measurement principles also we will get that for sampling techniques, right? Okay, so we discussed that the workplace air pollution will be determined using this one. So the complete measurement process comprises the following steps. The first thing is sampling. So, okay, we discussed this already. We have to do the sampling. So we have to collect the gas samples, and then if we have some on-site instrument or methods to determine the gases, it's okay. But if not, we have to transport these gas samples, and also we have to store it. Then we will do the analytical determination, and then we will assess the quality of this air. So those are the four major steps that involve in the measurement process. Okay, again, the sampling can be divided in this way. So the sampling can do without enrichment or with enrichment. Without enrichment, we can directly collect the sample using gas sample vessels, and also samples in original state. So, there are two ways. We can, here in the direct reading, without collecting gases, without sampling, we will feed it directly, or we can collect the original gas. And with enrichment, I think we discussed these things already. Adsorption or absorption. We have not discussed absorption in previous slides. It can be either absorption or reaction. So some electrochemical reaction or any other type of color forming reaction, or whatever the type of reaction can happen, it will come under enrichment. Yes, here again we are describing what is in that flow chart. So workplace air can be analyzed directly, and also it can be separated and enriched in the collection medium. So the gas is adsorbed to a solid collection phase or absorbed into a solution. So the adsorption, no absorption is possible, and chemical reaction or also possible. It can be the derivative formation also is possible. Okay, and again here also when we do the sampling with enrichment, if we do adsorption or absorption, then again this equation has some importance, because the sampling comes using this equation, the volume equals to flow rate times the sampling time. So this we can get some clue about the sample correction time, speed or volume. Okay, adsorption tubes. So for sampling with enrichment using adsorption tubes, the substance can be adsorbed onto a solid collection phase. After we adsorb using any adsorption material, then before the analysis, we have to desorb it, because the adsorption is only the technique of collecting sample. But before we analyze the sample, there should be some way for the desorption. The adsorbed gas should desorb into again to somewhere, right? So these adsorption tubes are heated in a compatible thermal desorber. So when we heat these adsorption tubes in the thermal desorber, the collected substance can transfer into a cold trap using a carrier gas. We have to use a carrier gas, so the adsorbed analyte will be transferred to a cold trap. When desorption is complete, the cold trap is heated and then it will transfer the sample onto the GC column for separation. So what is saying here in a nutshell, this is the idea. So once the gas analyte is adsorbed to the adsorption tube, we can heat it. When we heat it, the adsorbed gas will desorb from the solid phase. Then we can use this gas to the analysis, right? So here it describes thermal desorption, and there's another way, solvent desorption. See, this table shows the commonly used adsorbents and the type of desorption available. So the first one is the solvent desorption and the thermal desorption. Here in the thermal desorption, as the desorbing material, we use the temperature. We use the high temperature, and in the solvent desorption, we can use some kind of solvent which can replace the adsorbed gas. So these are the common adsorbents we use: activated carbon, silica gel, and borax. All these things are good examples of commonly used adsorbing materials. And the reaction sampler. So when we trap using a reaction, we use reaction sampler. So here, since the chemical reaction happens, we have to use reaction sampler. So the sampling can be used, we can use either bottle in which the reagent is dissolved, or with the sample media, filters or adsorbent that have been pre-treated with the reagent. So it can be a bottle or any other media, but that should contain the reagent which gas react with. So the reaction between the investigated substance and reagent take place in situ during sampling. So in the during the sampling, a reaction happens. These are some examples of the gas sampling collection using a reaction. So for example, the aldehyde, when we need to collect aldehyde using enrichment systems, we use the impregnated with dinitrophenyl hydrazine. So then the aldehyde react with it. Similarly, for diisocyanates collected on filters, impregnated with 2-methoxyphenyl piperazine, and collection of hydrogen peroxide can be done in a solution containing titrate. So those are some reaction entrapment examples. And the sampling without enrichment. This method can either deliver the result instantly or on the location, or can be tested in a laboratory. So even without enrichment, we can collect the sampling vessels or the bags, and we can take it to the laboratory and do the analysis. So here again we are using the tedder bags or the gas sampling vessel. This type of sample also use that if the air is permanently polluted with organic gases, we can use this type of sampling. And for the analysis of gases and vapors collected without enrichment, a gas-tight syringe is normally used for sampling from the collection device. So after we take the collection device, we can use some gas-tight syringe. Okay, and this is another example. I will quickly go through. This is again, we repeat the same thing. Here, except we will discuss centrifugal collector and also impingers later, because we have not discussed this one. Other than that, the sampling bag, the stainless steel container, all these things, we already discussed these things, how to do the sampling. So these are the different types of devices available to gas sampling. Okay, impingers. So this is the image of an impinger. So it has a special glass tube and it is designed to collect airborne contaminant by bubbling the sample air at a high flow rate through a specific absorbing liquid inside. So here we can bubble the gas and then collect the sample. The liquid used can then be analyzed to determine airborne contaminant level. So that's the same thing. After we collect, we can do the analysis. So air drawn into the impinge is forced through a nozzle, which is covered by a liquid such as high purity water. So high pure water is normally used in these impingers, and the polluted gas will dissolve in the liquid and it can be analyzed using a colorimetric techniques. Most of the cases we use colorimetric technique using like a spectrophotometer to detect the type and the quantity of the pollution. Okay, this is another way we have not discussed this one also, centrifugal collectors. So here also what is happening there, the centrifugation has been done in this centrifugal collector. The particles are removed by the application of a centrifugal force, and the polluted gas stream is forced into a vortex. The motion of the gas exerts centrifugal forces on the particles. So here, I think this image you can see the gas inlet is from here. The polluted gas comes from this side and the centrifugation happens. Then the cyclone moves and the larger particle will deposit on the side wall, and the clean air will go through the top of this tube. If you need this picture, this diagram has more clear picture. So here, the red one, this is the dirty air. The dirty gas comes from this side, and then because of the centrifugation force, this creates a cyclone. Then because of that, the heavy particles will deposit on the wall and it will goes down, right? And the dust particle, most of the cases dust particles are the heavy particles present available in the gas. So it will collect, and then here, from here, collected dust particles will go out, and the clean gas, this is the clean gas outlet. So clean gas can escape from here. That is how what is happening in the centrifugal collector. So those are the methods and techniques for gas sampling. So we discussed how to do the solid sampling, liquid sampling, and gas sampling. So these three sampling techniques are the major techniques and major things that we should know when we talk about the sampling in chemistry. Right? Now, let's move to some statistics. Even when we do the sampling, we have to have some statistics. Okay. If you talk about the errors, even not only when we perform the analysis, even during the sampling, errors are possible, right? So the errors, there are two types of errors: determinate errors or random or indeterminate errors. We will discuss these types of errors under chemometric parts in more detail. But for right now, the random errors has some implication, or it is a measure of precision, and the systematic error is measure of accuracy. So the accuracy is changing, it has some impact on accuracy if there's a systematic error. And the determinate error or systematic error can be reduced to lower value, and the remaining uncertainty, if we reduce the determinate error to a lower value, other remaining uncertainty of the result is due to random errors. So random errors can be quantified by calculating the standard deviation. So here the standard deviation of a method is composed of standard deviation of each step in the analysis. So in a method, if we talk about a method, standard deviation of a method is the standard deviation of each step in the analysis. So this is the equation that you can use S naught. That is the overall standard deviation. So we need to calculate the overall standard deviation. In order to calculate overall standard deviation, we have to take the SA squared plus SS squared. We have to add them together and take the square root of this summation. SA is the analytical standard deviation. So the analytical standard deviation comes when we do the analysis. There will be some standard deviation. That is the analytical standard deviation. And SS is the sampling standard deviation. So that's what we have to worry about here under the sampling, because the sampling standard deviation happens when we have some poor sampling techniques. So we can minimize this sampling standard deviation also by practicing some good sampling techniques, right? Okay, this equation, remember this equation, let's do one calculation using this equation. So look here, this question. If there's a particular analysis, it has been determined that the sampling error is 6%. A particular analytical technique can give a precision of 1%. What is the overall precision, and is it worth considering a slower technique which can give a precision of 0.2%? So that is the question that have been given. So what it says, there's a sampling, there's a particular analysis. In that analysis, sampling error is 6%. Sampling error 6% means the sampling standard deviation, or SS, is 0.06. And the precision of the method, precision of the particular analytical technique is 1%, right? That is the precision. And it asks whether, it asks us the overall precision. Overall precision means the S naught. We have to calculate S naught. Let's see how we can do the calculation. So using this equation, now SS equals 0.06. This is the SS, right? I think we have to switch these values. So SS is 0.06 and SA, it says the analytical technique have precision of 1%. When it says analytical technique precision is 1%, that means the standard deviation of this analytical method is 0.01. We have to divide this 1 by 100. So that's how I get the SA. Then when we need to find the overall precision, calculate the overall standard deviation. So the overall standard deviation, when you do this calculation, it is equal to 0.06. This is the overall standard deviation. This is not the precision, right? This is the overall standard deviation. It asks what is the overall precision. So just to find the overall precision, you have to multiply this by 100. Then you will get the percentage precision. And in the next part it asks, is it worth considering a slower technique which can give a precision of 0.2%? Now the precision is higher because the standard deviation or the error is 0.2. The standard here the standard deviation of the analytical technique is 0.002. Therefore, that means it has high accuracy, right? And then we have determined whether is it worthy to use this technique which has high precision, right? Now, for 0.2% analytical precision, we can calculate the overall standard deviation. If we calculate the overall standard deviation to 0.2% one, then instead of 0.01, we have to substitute 0.002 as the SA value, analytical standard deviation, right? When we do the calculation, now the value, the standard overall standard error is 0.06. If we get 0.06 overall standard error, is there a big difference between these two values? No, there's no big difference, right? This is 0.0608. If we use the more precise one, it is 0.06. The overall standard deviation reduced, but it is in the fourth decimal, so there's no significant difference. Therefore, answer is no. It's not worth using technique of higher precision, right? Because even though we use technique of higher precision, we are consuming a lot of time. But even though we are consuming a lot of time, we cannot minimize the error. Only a negligible amount can be produced. Therefore, it is not worth using this technique. All right. I have another question. So this question, this one, you can try this one by your own. So for SS, it's 15% and SA 5%. And if it's reduced to 1%, what is the, I cannot see, what is the total precision, right? You guys can do this calculation. I will give a 2-minute break, so because then we can go to the next section. So you do the calculation for this question. And also, if you have any question, please ask now. Okay. Okay, so this is easy. You just need to substitute values to SA and SS, but make sure you have to divide the numbers by 100 when it is given as a percentage. Okay, when this is the thing, when obtaining a representative sample from a bulk solid, extreme care must be exercised in order to reduce the sampling errors to a minimum, right? So when we do the sampling, we have to extremely care about the sampling technique, and we have to minimize the errors due to sampling. If not, the whole time and cost of the analysis will have been wasted. So that's the most important thing in the sampling. So that's all I have for the sampling. Then let's move to instrument performance characteristics part. I already uploaded this instrument performance characteristic lecture slides presentation also to LMS, so you can download it. Okay. Okay, I hope you can see this presentation also. Okay, now let's move to this section. Now it comes, earlier we just, in the sampling part we had only theory, but from here onward, all the maths come to the picture and all the statistics come to the picture. So even though we are using statistics and maths part, it's basic maths, right? So here we will learn some basic statistics that we need to use during the analysis of some samples. And the first thing, before we move to a particular analytical method, so first thing we have to collect sample. Okay, we learn about how to do the sampling. Now we know how to collect samples. Then after we collect the samples, we should determine which instrument that we need to use, because there are lots of analytical instruments and there are lots of instruments in the labs. So we have to have an idea about the instrument that we are going to use for the analysis, right? We cannot just say, okay, now I see the UVVs, I will use the UVVs. I can see the IR, I'm going to use IR. No, there should be some rationale for the selection of the instrument. From this performance characteristics, we will learn how we can select a particular instrument for a particular analysis of particular samples, right? So this is the heart of the analytical chemistry. Any analytical chemist should know these performance characteristics. Okay, so these are the numerical criteria for selecting an analytical method. We call them as figures of merit. So that word, you have to be familiar with that word, figures of merit. So these figures of merit are the numerical criteria for selecting an analytical method. Let's see what are these figures of merit. This table shows the figures of merit in chemistry. The first one, precision, bias, sensitivity, detection limit, dynamic range, and selectivity. These 6 figures of merits are really important, and you have to have a good and thorough idea about these figures of merit when you select any analytical method. right? The precision, we will discuss this in detail, and for right now, the precision. The precision can be determined using absolute standard deviation, relative standard deviation, coefficient of variation, variance. Here you have to have an idea how to calculate these standard deviations and variance. So when you calculate these things, you can get an idea about the precision and the bias. So bias can be determined by calculating absolute systematic error or relative systematic error. Sensitivity, there are two types of sensitivity. We will learn this in detail also. Calibration and analytical sensitivity. And the detection limit. The detection limit is blank plus 3 times standard deviation of the blank. No need to worry right now. I will explain all these things in detail in the coming slides. And the dynamic range, limit of quantification and limit of linearity. And the selectivity can be determined using the coefficient of selectivity. We will learn all these figures of merit and how to calculate those figures of merit in detail. Okay, any quantitative instrument performance criteria that can be used to decide whether a given analytical method is suitable for attacking an analytical problem. So, if there's an analytical problem, we have to find whether we can use this given analytical method for attack this analytical problem. In order to see whether we can use it or not, we have to use this instrument performance criteria. Okay, these figures of merits allow us to narrow the choice of instrument for a given analytical problem to relatively few. So, among a lot of analytical techniques, we can calculate these figures of merits and we can determine those precision, accuracy, sensitivity, all these things, and then we can narrow down the instrument. If there are 10 instruments at the beginning, okay, now we can narrow down it to a 2-3 instrument. So now we have to use this one from these 3 instruments. Selection among these few, because even though we can reduce the number to a fewer number, still we have to reduce and we have to select one analytical technique. So selection of those few can be based on this qualitative performance criteria. So these performance criteria are qualitative. The one we discussed, the figures of merit, those are quantitative one. We can get some value for those things. But here we have to consider this qualitative performance criteria also before we select one analytical method. The first one is speed. The analysis should be speed one, because if it consumes days and years, it's not a good analytical technique. So we have to consider about the time or the speed. And the ease and convenience. The method should be more easy. We should perform the analysis easily, and also it should be convenient. And the skill required of operator, that also matters. Suppose you did the figures of merit calculation and you came up with one analytical method. But if you don't know how to operate the equipment, you cannot use that one, because there's no point of using that method since you don't know how to operate it. Therefore, the skill required of the operator is also important. And the cost and availability of the equipment. That's the another most important thing, the cost and availability. So the cost, if it highly expensive one. So there's no point of doing the simple analysis. So based on the analysis, we have to determine, and based on the cost which will be needed, we have to determine whether it's worthy to use this instrument or not. And per sample cost, it's also a similar thing. For the one sample, how many what is the expense that we have to use, that will be used, so it's also important. So we have to consider these qualitative performance criteria also along with these figures of merit. Right? Now let's discuss each of these figures of merit, 6 figures of merit in detail. So because it's worthy to go through one by one, because it has really high importance. The first one is precision. The precision is the reproducibility of results, that is the agreement between numerical values for 2 or more replicate measurements or measurements that have been made in exactly the same way. So how we can reproduce the result. So that's the precision. Generally, precision of an analytical method is readily obtained by simply repeating the measurement. You know, even if you do a titration, even for the titration, you have to do 3 replication. So that's to see whether your method is precise enough. Okay, so the reproducibility of results is known as the precision. So you can see this image. So this x-axis is for accuracy and y is for precision. Here, if you see this one, the target is here in the middle, but the values are all everywhere. It's in everywhere. See the dot sign everywhere. So in this one, we can tell it has low precision because the readings are in everywhere. And also it is highly deviated from the true value. True value is somewhere here. But all these readings are really deviated. It's highly deviated from the true value. Therefore, this has low accuracy and low precision because the readings are everywhere. So low accuracy and low precision. If we look at this one, the accuracy, it is close to true value, right? So the true value is here, but all readings are around the true value. Therefore, it has high accuracy. It is highly accurate, but the precision is poor. The reason is all the readings are everywhere. So the precision is poor, even though it has high accuracy. And how about this one? True value is here, and all the data comes under this range. So it has high precision because the reproducibility is high. But even though it has high precision, the value is highly deviated from the true value. Therefore, it has low accuracy. In this diagram, it shows it has high precision as well as high accuracy. All the readings in the target and the values are all in line with the true value. Therefore, it has high precision and high accuracy. So this is the precision, the definition of the precision. And then let's discuss what are the figures of merit for precision. These figures of merit came under, I listed down in that table in the first slide. So let's discuss the figures of merit for precision in detail. The first one is absolute standard deviation. Absolute standard deviation represented as the lowercase s or simple s. So this is the equation we can use to calculate the absolute standard deviation. So here the xi is the numerical value of ith measurement. So for example, if it is the 10th measurement, the xi is 10th one, and the x bar is the mean of the n number of measurements. And using by substituting values for this equation, we can calculate the absolute standard deviation and the relative standard deviation. Relative standard deviation can be calculated by dividing absolute standard deviation by the mean value. And the standard error of mean is same equals to absolute standard deviation divided by the square root of the number of measurements. Coefficient of variation, that's the another figure for determine the precision. So we can divide the standard deviation by the value x bar and the multiply it by 100, and the variance is square of the standard deviation. So those were the figures of merit for precision, and you will do some exercises to find these figures. We will do it under tutorial. And the next one is bias. So this bias provides a measurement of a systematic or determinate error of an analytical method. The bias, this delta is for the bias. Bias can be calculated by taking the difference between the population mean and the true value. So bias can be calculated using this equation, and it provides a measurement of systematic error of an analytical method. And the sensitivity. So sensitivity is one of the most important things, and the sensitivity of an instrument or a method is a measure of its ability to discriminate between small differences in analyte concentration. That means if we use a particular method, if we can determine even a really small difference of the concentration, that method is highly sensitive, right? So really that's the sensitivity. So that's one. Just in general, that's the sensitivity. So that method is more sensitive for that particular analyte. And the sensitivity, when we do the when we go for the figures of merit, we have to have some way to calculate the sensitivity. We cannot just say, okay, we can determine even a small concentration from this method, so this is more sensitive. No, there should be a quantitative way to determine the sensitivity. So the sensitivity depends on the slope of the calibration curve and also the reproducibility or precision of the measuring device. Both these factors are important when we calculate the sensitivity of any method. So the calibration, slope of the calibration curve and the reproducibility. Here you can see this is one calibration curve. So the red one and blue line. If we talk about the sensitivity, higher the slope, the more sensitive. The method is more sensitive. Suppose this blue and red graphs were obtained using two different methods. So the concentration versus here the y-axis is a signal, analytical signal, versus concentration, right? So these two graphs were obtained from two different methods. When we plot the calibration curve, if the slope is high, this method is more sensitive. So in the blue and red graph, which one has higher sensitivity? Which one has high slope? The blue one has high slope, right? The slope in blue graph is higher compared to the red one. Therefore, the blue graph has high sensitivity. So the method, that blue method has more sensitivity. So if we select a method using these two, we have to select the method blue because it has high sensitivity, right? That's how we determine the sensitivity using the slope of the calibration curve. Okay, and even in the first table, I mentioned that there are two types of sensitivity: calibration sensitivity and the analytical sensitivity. So the calibration sensitivity is the slope of the calibration curve at the concentration of interest, right? So that is the calibration sensitivity. Slope is the calibration sensitivity. So suppose this is the signal concentration and S equals MC plus SB. SBL means the blank signal, the instrument signal for blank, and S is the measured signal, C is the concentration of the analyte. So when we plot this graph over the calibration curve, this slope M is the calibration sensitivity. Right? There is one disadvantage of the calibration sensitivity. By measuring calibration sensitivity, it fails to take into account the precision of individual measurement. So we cannot take precision of individual measurement by looking at the calibration sensitivity. Therefore, we have to go for analytical sensitivity. In the case of analytical sensitivity, it also accounts for the precision because this is how we calculate the analytical sensitivity. The gamma equals M. M means the slope divided by standard deviation of the measurement. Here we are considering, or we are taking or measuring the standard deviation of the measurement. Since we are accounts for the standard deviation of the measurement, automatically precision of the individual measurement comes under this analytical sensitivity, right? So even though calibration sensitivity has that limitation, analytical sensitivity does not have that limitation. So you have to have an idea, or you should know how to do all these calculations, right? I will cover this in tutorial also. Okay. Next figure of merit is detection limit. Detection limit. The name also says something. So the detection limit means the limit that we can detect. That's the most simple definition. So if we go for more scientific definition, the detection limit is the minimum concentration or mass of analyte that can be detected at a known confidence level. Let's say at 95% confidence level. So that is the minimum concentration or mass of the analyte that can be detected using a particular instrument. So that is also important, the minimum amount, because if the minimum amount is a really high number or the high concentration, we cannot go to determine smaller concentrations using that analytical technique. Therefore, the detection limit is also has high importance, right? This limit depends on the ratio of the magnitude of the analytical signal to the size of the statistical fluctuations in blank signal. Okay, now this limit, the detection limit, depends on the ratio of the analytical signal to blank signal. The ratio between the analytical signal to blank signal determines the limit of detection. For example, if analytical signal is not larger than the blank signal by some multiplication, let's say it's k, it is impossible to detect analytical signal with certainty. That's true. Suppose the blank signal. If any instrument, blank signal means there's no any analyte, but even without analyte, if the instrument gives some large signal, so that is the blank signal. So if the analytical signal, if the amount of analyte that we are using and the signal that is given by that particular analyte is not larger than the blank signal, can we identify the analytical signal? No, there's no way. We can't identify the analytical signal because the analytical signal is hidden inside the blank signal. Therefore, if the analytical signal is not larger than the blank signal by some multiplication, it is impossible to detect this analytical signal correctly, right? Therefore, the limit of detection is approached. When the limit of detection is approached, the analytical signal and its standard deviation approach the blank signal and its standard deviation, right? When the limit of detection approach the analytical signal, let's represent as SM. So SM is the analytical signal at detection limit. And SBL is for the blank signal and standard deviation for the blank is lowercase, simple SBL. When the limit, at the limit of detection, this SM here, the analytical signal equals to the blank signal plus some multiplication, the K, some multiplication of the standard deviation of blank, right? So, this is at the detection limit. So, the detection limit signal equals the blank signal plus K times standard deviation of blank. Normally, at 95% confidence level, the K equals 3. So, most of the cases, K equals 3. Therefore, at the detection limit, the analytical signal equals blank plus 3 times standard deviation of blank. This is what I told you at the very beginning. I will show this table again. See, I wrote here detection limit is blank plus 3 times standard deviation of the blank. Blank detection limit signal is SM equals blank SBL, blank signal, plus 3 times standard deviation of blank. 3 simple SBL. So that's what has been written there, right? Okay. See, this equation is important. So, when you need to know the detection limit, when we have to calculate the detection limit concentration, first thing we have to calculate the signal at the detection limit. So, how we can calculate the signal at the detection limit is we have to measure the signal of the blank and at the K, that means 3 times the standard deviation of blank to the blank signal. then it will give the analytical signal, right? Once SM and SBL is determined, detection limit can be determined using the slope. So you remember in the sensitivity, when we described the sensitivity, I showed you this equation. Analytical signal equals M times. So this SM, this is for the detection limit. Analytical signal at detection limit equals M times, the M is the slope, concentration at detection limit plus blank signal. So the concentration at detection limit can be found using this equation, because we know the signal, both signals, and we know the M or the slope from the calibration plot. So we can calculate the detection limit. So the detection limit is important if the concentration, the CM or the detection limit concentration is less than the blank signal, then we cannot use that particular analytical method. So if we choose some analytical method, the concentration should be higher than the detection limit concentration. Okay, the next one is dynamic range. That's the other figure of merit. The dynamic range is the lowest concentration at which quantitative measurement can be made. Limit of quantitation, right, to the concentration at which the calibration curve departs from in linearity. So usually the deviation 5% from the linearity. So the dynamic range, this graph shows the dynamic range. Limit of quantification, this is the limit of linearity. So the limit of linearity means when the graph, after a certain concentration, the linearity of the graph will deviate. You know, if you talk about the Beer-Lambert law, so when the concentration is too high and when the absorbance value is higher than 0.7, the linearity of the graph is also changing. That's why we are using the absorbance value 0.2 to 0.7 in the UV spectrophotometer. So that's, therefore, if we select any particular method, the concentration of the analyte should be in between this range. We call it as dynamic range. It should be in between limit of quantification to limit of linearity. So if the concentration is somewhere in between the dynamic range, we can use that particular analysis. That is the dynamic range. And the last one is the selectivity. So the selectivity is also highly important. The selectivity means the degree to which the method is free from interference by other species contained in the sample matrix. You know, if we do any analytical technique, some species present in the sample matrix can interfere with the signal. So if there are a lot of interference, then the method is not suitable. We cannot use that method for the analysis. Therefore, selectivity is highly important. Okay, let's see an example. So if a sample contains components A, B and C, then the total instrument signal is given by S. Instrument signal equals to slope times concentration of A, B, C and plus blank signal. So this is the signal for a sample which contains components A, B and C, right? And then the selectivity coefficient for A. Now it has three components, A, B and C. We are going to measure A, right? Then the selectivity coefficient for A with respect to B. We can show it as KBA. It is the ratio between the slope of B and slope of A, right? MB by MA, the slope. The ratio between the slope is the selectivity coefficient ratio. So the selectivity coefficient gives the response of the method to species B relative to species A. So here this one gives an idea about the response of this particular method to species B relative to species A. In the same way, we can find the selectivity coefficient for A with respect to C. So KCA equals slope of C divided by slope of A. Then we can substitute this KCA and KBA values here, right? So S equals MCA. And instead of MB, instead of slope of B, we can substitute KBA, MA, right? Instead of MB, we can substitute KBA, MA to this equation. Then when we substitute it here, it becomes, because MA is common to all, therefore we can take it out. Then KBA, CB. Similarly, instead of MC here, we can substitute from this equation KCA times MA. This one to here. Here to here. And KCA times MA times C. So we substitute it to this equation here, and then we can add the signal of black. Now we know the K values. We know slope of A and K, all these things. Then we can calculate by using the selectivity coefficient. We can determine whether we will be able to get a signal for A in the presence of other components. Right? Is that clear? This one? I hope it's clear, because if you have any question, you can either in the chat box, so you can let me know, then I will explain it again. Right? Okay, hope there's no any problem here. So then I'll move. So that's how we can calculate the selectivity. That is how we can determine whether a particular method is selective enough for the analysis, right? So even in the presence of three different types of component, so we have to determine whether we can detect the particular component. Okay, so far we discussed all the figures of merit available, so precision, bias, selectivity, detection limit, and sensitivity, and all these things. These figures of merit is highly important, and you have to have a clear idea about how to determine how to find whether any chemical method is suitable or not based on these figures of merit, right? And I have a question. So this is a simple question. You can practice this one. So for this one, when you solve this question, you need all the most equations that you learn. I will explain this question and you can do and you can find the answer by your own. And what we can do, if you have any issue, you can ask me, or if not, we can discuss it next day also, but I will explain what is asking in this question, okay? So this is the calibration curve for determination of lead based on its flame emission spectrum yielded following equation. So this is the equation. S equals 1.12 times C. C is the concentration. Thus 0.312. S is the measure of the relative intensity of the lead emission line, and following replicate data will then obtain. So these are the replicated data for 10 ppm. This is the concentration of lead. It has been done for 10, 1 and for the blank. And this is the number of replication, mean value and the standard deviation. All has been given. In the question it asks to calculate the calibration sensitivity and the analytical sensitivity at 1 and 10 ppm and the detection limit. Okay, and when you, let's say the first thing, the calibration sensitivity. So you can see the equation has been given. This equation is, this equals to S equals MC plus SBL, right? Which is here. I will go to that slide. Here. That equation is same. S equals MC plus SBL. So I told you here the calibration sensitivity is the slope of the calibration curve. So the slope of the calibration curve is calibration sensitivity. Slope means M. So in the question, the slope is 1.12. That means the calibration sensitivity is 1.12. So the answer is direct. So when you were asked to calculate the calibration sensitivity, it's same as the slope, right? And then the next one says the analytical sensitivity at 1 and 10 ppm of lead. So then you have to calculate the analytical sensitivity. Let's go and see the analytical sensitivity. The analytical sensitivity means the slope divided by standard deviation of the measurement. Right? Then here the slope is, what is the slope? It's 1.12. The slope is 1.12, and then the values, the standard deviation values also has been given. Then when we calculate the analytical sensitivity at 1 ppm, so go to the 1 ppm, this is the 1 ppm concentration, and that is the standard deviation at 1 ppm. Slope is 1.12, then divide 1.12 by the standard deviation. It's really easy. And when it comes to the 10 ppm, the slope is still 1.12 and divide it by the standard deviation 0.15. Right? So that is the analytical sensitivity. And the detection limit. When it goes to the detection limit, you have to go to that equation, this one. Sn equals SBL plus K standard deviation of the blank. And the signal at the detection limit, the signal of the blank, here the K, normally we use 3. K equals 3. Therefore, if it has not been stated, if it has not been given, you can use or you can assume K equals 3. And 3 times the blank, standard deviation of the blank. Now, the detection limit here, this is the blank signal. So when you calculate the signal of the signal at the detection limit, you have to use this blank signal. So lead concentration 0 means blank, that is the blank. So this is the blank signal, this signal plus 3 times the standard deviation of blank. This plus 3 times this. Then that will give you the signal at the detection limit. Then we have to calculate the concentration. Once we know the signal at the detection limit, we have to calculate the concentration. So use that equation. We know this one, and this has been given, and slope has been given. So here the calculated value minus the signal of the blank divided by the slope. Then it will give you the detection limit concentration. So you can find the detection limit. So it's really easy. So that's how we can calculate all the sensitivities and detection limits. Okay. Yeah, that's all I have to talk, because today we talked about the instrument performance characteristic. I think from next week we can start chemometrics part, because that's the one with lots of calculations. So if you have in here also, if you have any question, you can email me, or when we log into next week, you can text me. Okay, so I hope if you have any question, or I hope it is clear for you all. Okay, looks like no question. Any questions? Okay, one of you has texted me to explain it again. I don't know which one. Tashmila, if you are still there. Tashmila, can you please let me know which one I should explain? Are you available? Sensitivity. Okay, sensitivity. Okay, I will explain that part again. Okay, sensitivity. Here, I think because since we already discussed the question now, it should be clear, but I will quickly go through this again. So the sensitivity, I told the sensitivity depends on two things, right? The slope and the reproducibility or precision of the measuring device, right? Here, the sensitivity is high if the slope is high. The slope of the graph. If the slope of the graph is higher, that means the sensitivity is high. The red color, if we consider the red graph and blue graph, the blue graph has high slope. The slope is high. Therefore, the sensitivity of this method, the blue method, is higher compared to the red one. Right? So when it says, when you have been given, let's say 3 calibration plots, and if you were asked which one has the highest sensitivity, only thing you have to do is determine the slope. When you determine the slope, if any method has highest slope, then that method has highest sensitivity. So this is the important thing. Higher the slope, more sensitive, right? And the sensitivity, we have 2 types: calibration sensitivity and analytical sensitivity. So when it goes to the calibration sensitivity, same thing. Calibration sensitivity is the slope of the calibration curve. So when we plot the calibration curve, S versus concentration, and when we determine the slope, you know how to determine the slope, right? The y values, the difference between y values and difference between x values. So when we calculate the slope, that is the calibration sensitivity. But this calibration sensitivity, we are not taking precision when we take the calibration sensitivity. Therefore, we need to have analytical sensitivity. The analytical sensitivity, we can calculate analytical sensitivity by dividing the slope, this slope, by standard deviation of the measurement. When we use this equation, we will get the analytical sensitivity. So simply, the calibration sensitivity divided by the standard deviation, we will end up with analytical sensitivity. Right? I hope now it's clear. Is that clear? This, yeah, yes. Yeah, you can. I think this is too much. But what you can do, please go through the slides, because I already uploaded these presentations. So you can go through this presentation, and then if you still have any question, let me know. You can email me, and also I will try to upload the recording, then you can hear to the lectures, because it will be easy for you to understand. And then I will see whether I can upload this recording, so then it will be easy for you. You can follow the lecture and have some understanding. Okay. All right. So since you don't have any other question, let's stop for today, and let's start chemometric part next week. I will upload that one also before the lecture with the chemometrics. Please read the lecture material before you can. I'll try to upload it on before Monday. Okay. Okay then. Have a good evening. So see you. We will meet you. I will meet you all next Monday.